I'm Antonio Sala, and in this video we are going to discuss the simulation of the simplified equations of the phugoid mode in an aircraft's longitudinal dynamics. In previous videos, we discussed how to obtain the equations. They were based in a force balance and not in a torque balance, because we were assuming instant alignment of the body with the airspeed vector, kind of weather vane behavior. So under those assumptions, and setting for simplicity, lift being a constant coefficient times the square of the airspeed, and likewise with drag, at the end we were able to pose these four equations governing the phugoid dynamics. Note that the top two ones in blue can be independently solved of the Cartesian position ones, the bottom black equations. Also, in another video, we explained how setting some values for the constant parameters and the thrust and writing the state equation, then this ODE45 code was able to carry out the simulation. The objective of this video is trying out different lift, drag coefficients and thrust to try to intuitively understand the physical meaning of these dynamics. So we'll start with the first simulation, in which we'll use a lift coefficient of 1 and a drag coefficient of 0.667, which means a lift to drag ratio of 15. These parameters are arbitrarily invented, in the sense that I am not thinking in any particular aircraft. And also we are assuming constant thrust, but depending on the propulsion system, it may have speed-dependent terms, particularly in constant power propeller engines. But we are not taking those issues into account for simplicity and for lack of knowledge, also because I am not an aerospace engineer. So okay, we will start with this simulation and we'll analyze its output. If my starting speed is 4, 6 degrees upwards, and I simulate 20 seconds of simulation time, then this is the simulation we get. We see that there is an oscillatory transient, but such transient is stable, and the plane ends up descending at a constant speed and a constant angle. The angle is named the glide angle. This is the XY animation, and here we have a look at the airspeed in blue and the pitch angle in red. So speed stabilizes around 3.15 or something like that, and gliding angle stabilizes in -4 degrees. If we now look at the accelerations and other forces involved, the blue line is the modulus of the acceleration vector. It decays to 0, indicating that indeed at the end of the transient the gliding speed is constant and the path is a straight line. The red line is the signed normal acceleration, in this case for a normal vector pointing up, and changes of sign indicate inflection points in which the trajectory changes from rotating clockwise to counterclockwise or vice versa. As a last remark, if we look at the yellow line, we see that in the starting phases of the transient, lift is 1.6, let's say, times the weight of the aircraft. If this figure is excessive, then the wings may break if maneuvers are too aggressive. For instance, in this experimental testing, we can see that in here, in the upper part of the phugoid, the wings are not deformed because it's at low speed, low lift. So it's starting to fall. But in here, in the lower part of the glide, before starting climbing again, note that the wings are deformed because there is higher airspeed, so the paper plane bends and it's lifting with a much higher lift force than in the top of the glide. If I start with a larger initial speed of 15 units, then the plane loops, but as energy is lost due to drag, the dynamics is finally stable and we end up at the same gliding angle as before. And of course, when angular velocity is very high or linear speed is very low, particularly in here, let's say, maybe these simplified phugoid equations are not so reliable. But okay, the thing is that these equations approximately predict the looping behavior on a glider, because in here we are simulating zero thrust. Of course, in order to loop, we need a large initial speed. In here is just changing a line of code, but in real life, it may imply diving down from a high altitude. If we watch this video, we can see an actual glider looping in real life. So we will have it diving from high altitude and then performing the requested looping. Another interesting simulation is when thrust is equal to the drag to lift ratio times weight, because in that case it can be easily proved that that is the thrust figure needed for level flight. We'll start at lower speed to forget about loopings. And here we have the simulation, oscillatory phugoid, but stable, and ending up in level flight. We see here how the angle red line ultimately settles to zero, and how lift settles to 1 times the weight of the aircraft, because in level flight, lift must equal weight. If thrust is higher than this figure, let's say twice that value, then the final gliding angle is positive and the aircraft climbs at a steady climbing rate. But the phugoid mode is less damped. It takes longer to settle. In here we have simulated 20 time units and still didn't have the time to settle, but we can see that it's stable, so it will ultimately settle to a constant climbing angle. However, if we exceed a given amount of thrust, then phugoid dynamics becomes unstable so this is usually undesirable, and maybe in real life the airplane would crash. In here we can see oscillation of increasing amplitude and then later on just these loopings, but of course unstable behaviors, at least at first glance, are not so desirable in gliders or passenger airplanes. Finally, as a last simulation, if I return to zero thrust and I put lift and drag to 0, then the only thing we have is a particle that moves according to the weight, so we will have a ballistic trajectory, a parabolic one in this case. So that we would not actually need this phugoid stuff. We could study this movement with high school physics and parabolas, but it's interesting to see it as a particular case. Also, as a last simulation, if drag is higher, then there is more energy loss. And usually the behavior is much more damped, so it's more stable. You can see here how oscillations disappear in a couple of seconds. But of course then the airplane is less efficient and we need more thrust to keep level flight. So it's kind of trade-off, stability versus efficiency. But okay, there are many design issues when designing the airframe body, type, size of wings, gliding angle, gliding speed, efficiency, etc., that are clearly out of the scope of this video. So we'll end up here. In this video, we saw how the phugoid mode equations behaved in animations and in time plots. We simulated different thrust and lift to drag ratios. We saw that the phugoid mode is usually oscillatory and stable in zero thrust downward gliding, but it gets unstable for high thrust, at least with the chosen parameters in this video. And of course, phugoid equations, if lift is set to 0, reduce to ballistic trajectories. So this is it. We finish the video here. Thanks for watching.